Zoom. Today, we'll also only have a slides. I already posted and I call it annotated, so I'm not gonna write anything. It's mostly me talking about things. Okay, hello everyone. Welcome back. Thank you for being here on a Friday, really close to the finals. I know it's not easy to pay attention to lectures anymore. Most of that you have all of your grades already out, so I really appreciate you being here. So this week, like today, we'll go to Path Planning 2. You'll have to do an in-class quiz, which needs a passcode, so you can't take it right now. And then class participation 25 is due on Sunday. It's there used to be a programming assignment in previous semesters. I changed it a little bit, made it more like a smaller class participation to just play with RRT algorithm. So you're using MATLAB to do that. And you basically have to observe. So when you open it, it might look confusing or like big, but it's not. I will talk about this at the end of the class. Homework 5 is due on December 8th, which is last day of classes. And your final project is due on December 12th. Some of you already submitted your solutions. I will grade you next week. And so the sooner you post, the sooner you get your grade. All right. For next week, week 16, there will be class on Monday. I see it as a bonus class. I will talk about potential field, which is another way of path planning. I'm also debating if I should talk about Kalman filter. So I'll decide which one to go. Maybe I touch base on both of them. So Kalman filter is just a good way of mixing sensory data that you have, estimating a position and a state. I think at least I'll talk about it. So think of Monday as bonus class. So it's optional. But if you are not in class, please complete instructor exit survey. It's just basically a few questions about the class. Rather than SCI, I'm relying on my own survey and ask focus question, how can I make this better? And it's anonymous. You would automatically get points toward your class participation. And I would know positive, negative comment, be decent when you're giving negative comments, be constructive. If you find a problem, tell me, what do you think the solution is? And then I put them together. I've been changing this course many times and listening to what a student wanted. Sounds good? All right. Now, since Zoom is weird, I have to keep getting out of this and share a different, should be good. So a quick review of last class, height. We talked about path planning in general, and we said that path planning, basically the goal is to find a collision-free path from a start state to an end or goal state. If you remember, we covered two types of path planning or search. One was uninformed search, the other one was informed search. So when there is uninformed search, we don't have any information of our environment, right? So we kind of do a brute force kind of, follow brute force kind of algorithm, right? To search the area. So last class we talked about search, and then after the search is done, the algorithm can find shortest path if it knows where start and goal is, right? Generally in search, you'll find all the possible ways or kind of sweep the environment. The other method was informed search, that you use some sort of evaluation function. So there was a little bit more information involved. Which one was faster or less complex in terms of computational complexity? Uninformed or informed? Informed, right? So the idea is, so you always can use uninformed search and search everything. Do you remember what was the complexity of uninformed search? For example, in breadth first. So all the vertices plus all the edges, because you have to visit everything, right? So in uninformed. When we had informed method, then there was some priorities, right? So you didn't have to do as many search or visit all the edges and vertices, right? Now, that was the case when you had nodes or the wedges and then the vertices. Like, what's wrong with me? I think I'm hungry. The vertices, right? And then you would do the search. What if we don't have that? What if we have a continuous space? Because both of those are discretized, right? So you have nodes, and then you can go and search. What if we have a continuous environment? What do we do? Discretize it, right? So you discretize it, and then you can use the method that you already know how to use it. So we're gonna today look at how to discretize. There is a very specific method that you could use and discretize our continuous environment. All right. So before we start today, you can take the quiz and class quiz. It's kind of review of last class. I just have to share with you the passcode. Not 25. No. Go here. I think it's RT 2021. Just want to make sure. So the passcode is RT 2021. You don't have to take picture. Just type down in your quiz. Don't send it to anyone else. If you're here, you deserve this point. Don't look at your lecture. Try to see if you remember. All right. So passcode RT 2021. RNT in caps. There are 5 questions. You have 2 attempts. I'll give you 5 minutes. If you're watching in, when you're watching in Zoom, you can skip 5 minutes. No, use your mouth. It's okay. You can come. All right. 2 more minutes. You have 2 attempts. So kind of use the first attempt if you have doubt in something, and then use the second attempt to answer them. Okay. Let's see. I'm gonna turn this off so I can see how many of you have answered this. Yeah. Okay. So 74 answered. If you haven't finished, do so in the next 2 minutes. Average of 91. Good job so far. Is this still working? All right. All right. Let's see how everybody goes. Solutions. All right. So 97. Okay, great. So which one of the following algorithm is an uninformed search? Breadth first is the correct answer. Which one of the following algorithms is an informed search? Greedy search, which Dijkstra and A-star are type of greedy search algorithm. The breadth first search for a graph is a method to visit every vertex and edge exactly once in a well-defined order. 100% right. Dijkstra algorithm visit all the vertices regardless of the cost of its adjacent vertices. Wrong. What's the problem here? It considers the shortest path to the adjacent, right? So that was the problem here. So that's why the difference between informed, uninformed, it has the knowledge of the shortest path. It will visit the shortest, yes. Doesn't have to necessarily visit all. Were you here last class? So we had some of the, Michael asked, like some of the vertices that never were visited because of the cost of between the two. You don't necessarily need to visit all of them. You can check the lecture and there's a great example you can see. A-star algorithm uses a similar approach to Dijkstra, that's correct, with the addition of a heuristic function giving priority to nodes with lower cost. That's correct. You remember for the same example, if, for example, we can use Euclidean distance, right? X squared plus y squared, so have some knowledge toward the point, and I showed a video that how the two different algorithms perform. So A-star has more knowledge than Dijkstra. Does it mean necessarily it is more optimal? No. Depending on the obstacle. So in the exam, in homework, you'll explore that. All right. Okay. Speaking of homework, some of you already submitted, and one thing I noticed is that when you were explaining the observation, you didn't give much information. So you're ingenious, you want to be objective. So that website has time and distance between the two, like how long it took. Use those information when you're writing your observation, right? So at the bottom, you can say it on the bottom right or bottom left, it tells you total time and the distance, I think. So you can use that information when you are trying to explore the difference between the two algorithms. You can even use different obstacles and have like a worst case scenario. If you put two walls straight down, you'll see that the two algorithms react very differently. All right. All right. Hopefully on Zoom, they will see this like that. Well, most of you are here, so I should not be worried about Zoom. All right. So in the other method, when we have a continuous environment, we can discretize that, but it's a little bit different from what we had seen before. In this method, we are using sampling, meaning that we pick sample nodes in the free space that's provided and try to find path in between them. So in the sampling method, there is a function that randomly generates sample points, there is no such thing as randoms. There's always a bias, right? But let's say random, like very lightly, say random. So it generates points in that environment. And then there is a function that evaluates the samples in the free space if the samples are actually in the free space or in the occupied space, right? Because the sample might end up being on your obstacle. So a function has to compare these two, and then there's a function that will determine the closest node to the previous node. So in this method, the algorithm creates different nodes and kind of draw a tree kind of thing or a map, go from one node to the other, start branching out until it reaches the goal state. So there will be a function that finds the closest path to the next closest distance to the next free space available, and then there is a planner that will connect all of them and moves forward, right? So you'll have to have all of these 4 type of function in this kind of algorithm. Now, this process creates kind of a graph, and you'll see in examples. We start from one node, kind of literally branching out until we reach to the goal state. There are, so the one feature or one of the properties of this method is that this method will find all the feasible motion, all the feasible path from goal, from initial point, initial state to the goal, but it doesn't necessarily find the optimal path, but it will definitely find the path to go from one point to another point. So satisficing does not have to be optimal, but it will be an acceptable solution, right? So when you're using sampling method, be aware that if we have to have optimize, we need to do optimization as well. On its own, is not going to find the most optimal path, all right? You will see that there are methods that the same algorithm has been optimized to actually find the most optimal path, sorry. 2 major classes of samplings are rapidly exploring random tree, RRT, or probability roadmaps, or PRM. You might have heard of both of them. We will explore how do they work kind of in algorithm level, and I'll show you a few examples. One of them, the RRT, is your class participation 25, that you will explore the algorithm yourself. For RPM, I have given you the link, the MATLAB code, the same thing, but using our PRM. So I chose RRT for your class participation. So RRT is implemented using the tree structure that grows a single tree from a start point to a goal point. The procedure is you will find samples, so that generates those grids that we don't have, the nodes that we don't have, then finds the closest or nearest node, which was the second function we said this method algorithm they will have, then moves one small step, and then looks at the other nodes available. The nodes are sampled randomly, right? So depending on the function you write, how you get that random point node, then it finds again the shortest, moves forward. So it's planning that. It might find different direction from where it started, so kind of like a tree, but it's saving the information. There is a shortest between nodes, right? At the end, once the tree branch reached to the goal, then it will say, okay, now this path, well, the planner will say, this is the path that you can take, and will take you from initial point to your goal point, or initial state to your goal state. Then if there are obstacles, then it will avoid. So now the planner will find the shortest, right? Because the path between this sample point to this sample point, you can't find any kind of direction here, right? The path. It will find the shortest path, which is a straight line. Now, if you have obstacle, it has to go around the obstacle. We'll see some examples and see how it will deal with the obstacles. So when we have a new X, the next point is our goal until we reach the actual goal. So here you have to start from this start point, find different ways to get to this goal. So if you look at the pseudocode, at some point at the beginning, you have to do the sampling, right? samples from X, you introduce what X is. This is you're generating randomly all those nodes in that environment. Then you're evaluating what's the nearest. So define maybe Euclidean space, whatever that is kind of open. You can use any function that will find the shortest path or closest path. Then there is a local planner. So it's not a global planner. What does local planner mean? You are currently in this state. There are a few nodes that they might have the same distance or still in a range that can be considered a short distance, like your closest. Then the local planner will just find the path to those nodes. And as the algorithm goes forward, the local planner now is finding the next, right? Global planner at the end will say from the initial point to the final point, that will be your path, right? So that's kind of different. Terminology is important when you say local planner. So we are in our local area, the nodes around it. Then there will be an update. So move, if it is collision free, yes, no, yes, move to the next point, update all the nodes, do all over it again until this tree grows. Now, there are few other versions of RRT. One is the bidirectional RRT. You'll see why this is a better method, right? Why do you think the bidirectional RRT could be faster than usual RRT? Bidirectional means that from the state, the start state, grow the tree. From the end, goal state, grow the tree. Let's see where they meet, right? So do you think this will be faster? Why? So half the distance, also the other one is finding. So you're using the same function inside your algorithm, right, for closest. You're using the same local planner. So they're kind of, you're dividing the problem into parts, not necessarily equal, right? Depending on the obstacle in the course, one might reach faster to the other side, but you're kind of solving it from both ways. So this will be faster version. I will find the exact path between the two. The other one is RRT star. This one will optimize. So here you will have this optimal solution. Now, it kind of updates the edges of the tree. So this is if you use RRT, in this obstacle course, start point, end point, kind of finds all the ways until it reaches. RRT star, you'll see it find a quicker way. It tries to update all the tree with respect to so it has an optimization function inside of it. So then this will give you the optimal solution. You might even use another optimal optimization solution in it and find a better path. Because this is definitely a path is acceptable. It going between obstacles, not hitting, but is not the shortest. Now, when you're optimizing, you're not optimizing always with respect to distance, right? Sometimes, depending on what's important for the project, for the work, maybe time is a factor. So when you're optimizing, you optimize with respect to time. So defining cost function and then optimizing for that. Makes sense? The difference between them? But they all use the same concepts, right? Sampling, finding the shortest distance, local planner, advancing, updating, and repeat, rinse and repeat. You can follow this link if you want to get, there is a video that you can see how this tree is built. You can use that. Now, this is an example for a 3R robot manipulator. So this problem is that there are boxes on one side. The robot has to bring the boxes to the other side. Just kind of pick and move, right? Pick an object, move an object to the other place. So RRT will find a path from the top row and brings it down. RRT star finds the most optimized path and brings it down to the point. There's a short video of RRT star, and the other method, PRM, of the same problem that you can watch. I think it's useful if you watch it. If you're interested for your 2R manipulator, you can write an algorithm for pick and move objects and use one of the other methods. Yes.
For the algorithm on the right, there's a lot of like these sort of where you go into one switch very rapidly. Like the second, third,
Let me go back here. Okay, which one? So these green points are the nodes that it found and going through. The blue points, these are the robot arm. So it reaches to the singularity and then you see the next state. Yeah. So you know that when you have a robot, there is a singularity, right? So that point that you saw was a singularity, kind of jump. And you don't want that motion, right? Oh, what happened here? Okay, I have a YouTube video of that. Let's see if we can play that one. Using Build Robot, this is actually really interesting. I think my computer, yeah, went crazy. Share on.
Hey, it's Ryan Reynolds. So owner of Mint Mobile, my goal is to save our money so we can save you money.
Yeah, well, I like him, so why not? I was not planning to. All right, so there is a robot, a mobile robot. We already discussed dynamic in planning a robot, and this is your end goal. Thank you, OSU Wireless. And all of these are the path that the robot foreseen to get to the goal. The path that is highlighted and has points, these are the nodes that finds the best path. They're bringing obstacle in, as you see. So this is real-time robotics for those of you that want real-time, huh? And then look what happens. It updated the path because it's finding, it knows all the nodes, right? That now the problem is the shortest path and local planner has to find how to get to the goal. So as they say, that eventually it actually goes through them. This is a longer video. Yeah. So they're changing the goal. The goal is yellow. Okay, so that's LiDAR right in front of it. You see the light, the one in front of it, LiDAR. And then this little things, these are markers for the camera. So there's actually a camera system, the kind of GPS for indoors. So because of that, when the robot is here and the goal is behind the robot knows where the goal is. It's not actually seeing it, gets the position through the camera system. So it has a GPS, that's a location for the goal, for the obstacle. But the robot is capable of maneuvering in dynamic obstacle course and also changing goals. So if the search is complete, it has the knowledge, you can change the goal state, and the robot should be able to find the path to the goal state. Yes.
So like each of those little like branches that are like not taken, that's where it drops the sample point. And then
so all of those are sample points, but it's not taking them.
Yeah,
it's rejecting them because finds the shortest path. That's the planner that decides which one is the shortest path. This is dynamic obstacle course. So you see that it goes. So what does this remind you? On campus, Grubhub, poor Grubhub robot. How many times you've seen someone is in front of it, Instagram videos, and blocks the poor thing? Human have too much power. If robots come in, I think they deserve to punish it a little bit. I feel bad for the robot. So I think this is the game of chase. And what's happening here? So this is LiDAR. And these little things are for the camera, and this is the brain, which is open. And I think at the top, there's an antenna. It might be the Wi-Fi module, so I can actually get information. That's the student in purple, and that is the Grubhub robot. How many of you have done it? Be honest. Oh, you have done it too, okay. I haven't, I'm proud of myself. Or I'm afraid, I don't know. Maybe I was scared to do that. No, I'm thinking if eventually robots get the power, at least I didn't do it. So they're not gonna do it to me, you know? Karma, I believe in karma. All right, so you see that this guy is also finding its own path, right? It has another path. So they're giving goals and it's planning his path and it's getting worse. Like in Minecraft games right now. Minesweeper. Okay, all right. Too much fun. You can watch that later. Yeah, too much fun. We don't do fun here, do we? We do fun. All right, where was I? So I'm hoping that the Zoom can actually see all of this. I tried. Most of you here, so you should not be watching Zoom lecture, but if not, all the links are there. All right. So the other way of planning the path when you are in a continuous environment that you have the obstacles is using the probability roadmaps, kind of work based on the same principle. But then you are going to, in this method, define that free configuration space, like where you can actually, the robot can move, sample the points, and then create local trees from the point that you were. So all the sampling points are gonna start creating trees and finding closest to themselves. And then, so these little branches connect to each other and then create the tree. It's kind of faster, right? But as like imagine like creating, this is supposed to be whatever we're not. This is a GIF. Yeah. So kind of you see, so there are points here. This is growing on its own. This is growing on its own, growing on its own. So all of them are growing. They connect to each other, create that network, and then the planner can find the fastest way. Now this is the link mobile robot PRM in MATLAB. It's interactive. You could use it. It has a map that you can play and change some of the factors and then create different paths and see and observe how it works. A little bit more in detail, if you wanted to know the procedure, what actually this method will do. Let's say you have a free space, you have to give this free space map to your algorithm, right? So this is informed, we know the map. You have to give the obstacles, then starting to sampling points randomly, again, random treated lightly, is not quite random. There are some points sampled, but they are not in the free space. So this is free space, the blue ones are not, they're obstacles, so these are all rejected. Once the algorithm has enough samples, it chooses all the black ones that are, the red ones are rejected, the black ones are accepted, started growing trees, connect to K nearest neighbors. So you define what K is. So you want to connect every 3 of them, you can do every one of them, to really depend on the algorithm, right? Think about the complexity. So the more of these parallel you're doing, you're also making it more complex, right? But it will give you a faster solution. Yes, Michael. So you create number of samples. You'll say that this many samples, depending on the GPU you're using or the accuracy that you want from this, right? So creates those samples. What was question 2?
And then how do you know that when you draw a line between the nodes that are created, it's not going around?
So remember, there's a function that finds the closest path, and then there's a function that makes sure it's not going through the obstacles in free space. So you still have those 4 functions. So sampling, finding the closest path, if this path is available, meaning that it's not going to cross over the obstacles, right? And then the local planner connects them, so all of those now are connecting to their neighbors if your K is 3. So this is the local tree, right? Connecting, so eventually all of them become connected to each other. Next phase is query phase or finding a path, the shortest path between. And now you see that maybe this was faster to go directly from here to here, right? So there's always a smoothing algorithm that try to smooth it to find the shortest between, is there, because you have the, when you're sampling, you have the x, y, if it's in 2D of those points, right? So you can have a function that can find, is this the shortest? So if this was not the shortest point, smooth it out. So the fastest, the smoother point is now the green one, the path. Now this is the smoother. And you see that this might not, even this might, there might not have been a point between them, right? But assume that I'm using Euclidean space, there must be a path between these two. So it defines it. Make sense? So I don't have to be worried about your sample. That's why you can use random. Because later on, you're using a function to check the shortest distance. Yes.
But that's sampling, it is like a random mathematical problem. There's nothing physical about it. Like it's not physically like checking with a single point.
So this could be the map of this class, right? So everything is mathematical, right?
Like in order to choose like which point is getting sampled, that's just like a random.
It's random. The random function you define. You could have a function how to pick those nodes, right? Because at the end, it doesn't matter. You're going to do the smoothing part. And if you didn't pick a point here, you eventually go draw that line, right? So kind of to get it started, find a path and then see, okay, from this path, is there a shortest version that I can go? All right. So yes, mostly mathematics. I think that's the answer to your question. So this basically is the whole idea of the probabilistic, and you see that you really don't have to have all the nodes. You just need to have a series of the nodes and then find the path. So this is kind of the optimization that's happening here, right? When you see smoothing, you're kind of optimizing the problem. Now, for your class participation for Sunday, I have given you instruction manual. I've given you the XML file, which has all the code, copied from MATLAB. I didn't do it myself, but you can use that. And then there is a grid. So you have the matrix for this. All of them are in your class participation file. So you will open that. There's also a worksheet that I've asked a specific thing. So we're going to go through those now. But from here, you just have to do it for Sunday. By Sunday, you can even do it now. Stop sharing. Let's see. This is fun. We're not doing fun. Joking. You're doing fine. Okay. So I was smart. I prepared the MATLAB. So MATLAB online is open now. It's one thing is smart. So download. So it was a PA6. I didn't change it. It was previously a programming assignment, but for you, it's just class participation. Download MLX. Download the grid map. So both of these you have to put in the same folder in your MATLAB directory. Then follow instruction in RRT example document. Then you have to use this worksheet to report back to me your observation. Could have been smart to open that one as well. But in my defense, OSU asked me to update my Windows last minute. So it's kind of like, I'm not gonna make it to the class. So part one, I'm asking you to change the minimum turning radius of the vehicle, of the car. So the car is going to go through the tunnel corridor of that building. So by changing the radius, you have to observe what happens to the path chosen. 0.5, 1, 1.5, and 3. And then I want you to find a few more and find what is the smallest radius the car can go through the corridor. That was like actually the question you asked. If there was a hole, if the space was not enough, would the car go through or not? That kind of answers your question. All right. So what would you do is when you get the map, you put a screenshot of your path here for this and for this, and then fill this table, minimum turn radius, length of the path. All of these are coming from that code, number of iteration, number of generated points, and then I want you to describe your observation, what you saw from this. For part two, you see part one and part two in that Word file. Same thing. Then this one is about maximum connection distance. Fine. So here you copy paste or screenshot of the map, and then fill out this table and describe your observation. Now, Zoom is seeing this? No, it's not. All right. Can't wait for COVID to be over. All right, so when you put that in your file, when you open, you'll see this. So once you run, this occupancy grid will open up. And then I want you to go through the code and understand what the code is asking you. All right, or how's the code written? You don't have to write the code, but I want you to explore to understand what the code is about. And then, so right now, mine is not running, but you should be, because I'm not in the folder. You'll see that there will be a path generated from this point to that point. Where do you change the radius? Here, R, the radius of the start to goal. So if it is 6, I'll run. It's supposed to run. It will run for you. Then there will be a path. You copy, screenshot this path, and put it in the worksheet, right? What's that? RT example. MATLAB. Oh, good thing I copied it from MATLAB. But the thing that I wanted to explain, there, that one. So is this one. Open in MATLAB online. Now it's going to open. The weight is killing me. Okay. Now, okay, here. So finally, you see a map. So the map, so the tree is grown, the path is marked, right? So this is for whatever radius and distance was set. Then you will change the radius and distance, and then you get a different solution, and then you post it in your worksheet. All right, then you tell me your observation. So go through the code to see where what it's actually doing. Now you will see that for finding the shortest, the shortest radius, the smallest radius and shortest path, is using Dubin's car dynamic. I'm not like expecting you to know Dubin, but basically, so this is an interactive also. So here are minimum. If this runs, so nothing works right now, but it's fine. But if you have two cars, if you have a car from starting one point and you are supposed to go to another point going around an obstacle, for example, what is the minimum radius that your car or your object can take to go from this point to the other point? So this is a whole different dynamic. It uses an underwater vehicle and an autonomous robot. Wherever you need to take, you need to turn, go around an obstacle, go from one point to another. You can change plane, so you can move in 3D space. So for my project, my PhD project, the glider had to go down, turn, and the shortest path with the tightest circle was using Dubin dynamics. So the code for turning minimum turning radius is using Dubin. So when you're reading the code, it says Dubin, and that's the idea. So I pulled this up, but for some reason it's not working. So I tried. Trust me, does not want to work. It did? All right, thank you. But okay, there. So it goes from here and then basically finds all the circle possible it can go and finds, because physically you will be limited by the radius of the turn that you can take, right? So have fun exploring the code here. Don't forget observation. If you couldn't open, just plan mobile robot path RT MATLAB, you can find it. And thank you, everyone. Have a great weekend.